Good morning. So first video is talking through some of the stuff which you did last lesson. So really impressed those of you who sent me pictures of your Palaeomagnetism seafloor spreading diagrams. They were fantastic. And I have sent a couple of those on to the lady who does the marketing. So they might end up on social media at some point. So well done. They're really cool, really different. I hope you found it vaguely fun as well. But the whole idea of that was to kind of prove that certain processes are happening. So the fact that we have actually found those rocks underneath the sea gives us certain proof that plate tectonic theory isn't just a theory and it is actually happening. So the idea is, let's go back a stage, is that underneath the Earth's crust and lithosphere, we have these convection currents. So nice hot magma rises to the surface because hot things are less dense. It then reaches the surface and starts to cool because it's away from the heat source in the centre of the Earth's core. So it kind of spreads out either way and then sinks back around in these big kind of convection currents. We talked about this a bit at GCSE, those of you who did GCSE. We talked about this in the context of atmospheric airflows, and we'll be talking about those when we do tropical revolving storms in a bit. So these whole convection currents kind of occur quite regularly in geography, and again when we do tropical rainforests, water and carbon cycles next year, again we'll be talking about this kind of up and down motion of air, or in this case magma. So we've looked at a few different theoretical ideas. One idea is slab push and slab pull. So we have at this sort of point here and here, the idea that as we get new materials erupt on the surfaces of these volcanoes, the new land being created pushes the two plates apart, hence the term slab push, which I think you investigated last session. And then where we get plates being destroyed and pulled downwards over here with the downwards motion of the convection currents, we believe about here and about here, we have this process called slab pull. And that is the idea that as the plate descends underneath into the mantle, being sort of dragged down by these large forces of convection currents, it pulls the rest of the plate behind it. It's a bit like if you were to push a piece of paper off the edge of a table, the beginning part of the bit that's going off the table, as it falls, will pull the rest of the piece of paper along behind it as it falls over the edge of the table. So that's kind of the rough idea. So going back to this point, this idea of seafloor spreading. So we've kind of got this idea now that as these convection currents and slab push and slab pull are causing these plates on the surface of our planet to move apart or sometimes move together, if they are in general moving apart, we're going to get the creation of new land. So we get this kind of area in the middle. If you imagine the two big slabs of rock are kind of moving apart, we're not going to end up with a hole where you can just look into the interior of the Earth. That weakness, that area of weakness as you pull the plates apart, will only be a very small crack in reality. But as we create that area of weakness, we allow this magma that is rising to then sort of work its way through those cracks and erupt, forming sort of underwater volcanoes. Now we mostly get plates moving apart where we have two oceanic plates. So this plate here will be oceanic, this plate here will be oceanic, which means this is obviously going to be, let me grab my blue pen, it's all therefore going to be underwater. So we have these underwater sort of volcanoes, which we call the mid-ocean ridge, and you'll often see that labelled as MOR, and I believe you labelled that on your little diagrammy thing. So this rock here is all created as those two plates move apart, area of weakness, the mantle material then erupts as lava. As soon as it's erupted, it becomes lava, hardens and creates this rock. That's only part of the story as you started to investigate. So Harry Hess was the one who kind of discovered that we have these underwater ridges, and when they then went and took rock samples from underneath the ocean, they worked out that these rocks actually mirror the Earth's magnetic field. So if you went underneath the ocean, and we've got these sort of areas of volcanoes in the centre, and we've got these two plates over here which are moving apart. There we go. All this rock, if you look at it from above, so I'll just get rid of those for a second now, attempt to draw a 3D diagram. There we go. Lovely. So these are all this is all the material that's erupting here. So it's volcanoes. There we go. They worked out that the rock that was closest to the actual sort of line, if you like, where the two plates are moving apart, actually had a mirror image either side. Now you can't see it because you can't see iron particles. If you go back a little stage, we said that in the interior of the Earth, most of the inner and outer core is made up of a large amount of iron and nickel. The mantle is made of other elements, so you've got things like silica in there, but you also have lots of metallic elements too, iron being one of them. So when the material erupts on the surface, all the little iron particles do something really cool. They will line up and face whichever way is magnetic north. It's a bit like, you probably did this at school with a little science experiment, and you had like a little Petri dish thing like that, and you put iron filings in the bottom, and then you put a magnet over here, and all the iron filings would line up with whatever the way the magnet was. So that's the way that iron behaves, and it does exactly that in the rock. So all the rock that is here, say at this particular time, magnetic north was the north that we know, upwards. All the little iron particles will all line upwards to magnetic north. Now, this is where it gets a bit weird. Sometimes magnetic north is not the direction that we think of as north. Every couple of 100,000 years, and there's a lot of debate, if you Google it, it says 200,000 years. If you look at the textbook, it says 400,000 years. We don't really know. We're a bit in the dark about the timescale. The magnetic pole actually shifts. So what will happen, it doesn't sort of suddenly shift from north being north overnight to north being south like that. But if you were to hold your compass slowly over a period of thousands and thousands of years, magnetic north would actually not be north anymore. It would start to slowly go around towards the east or towards the west, and eventually it would end up facing exactly the opposite way, and it will stay the opposite way for another couple of 100,000 years until it then flips back northwards again. So what we found when we actually analysed the rock that's underneath the sea is that we get a band that will be magnetic north, and then we'll get a band that will be all the iron particles will be magnetised south, and then again you'll get bands are magnetised north, hence why you put up and down arrows on your little diagram as you pulled it out. So we know that all that does is it proves that the poles flip. It doesn't really prove plate tectonic theory, or does it? So what they found is that along the mid-ocean ridge, one side of the ridge would all be aligned north. They also found on the other side an equal worth of rock would all also be aligned magnetically north. And then again, they'd find a band about the similar width as this one here, where everything was aligned magnetically south. Now what that does prove, that proves that this rock here and this rock here, and they've actually gone down and carbon dated them too to find out that this is true, were both created at the same point in time. They're both aligned the same way, and they're both the same age of rock. So what that says is that both of those lines of rock were in the same place when they were created. And the only way that could have happened is if they were created here at the same point of time and they moved away from each other at a similar speed. Now, again, if you go, I don't know, a kilometre out or something, it will suddenly change. And that happens exactly the same, both sides of the ridge. So that itself is proof that plate tectonic theory must be true. That proves that our plates are moving at a similar rate in different directions, and that these rocks were both created at the same moment in time and have moved away from each other. So it's not just us saying, oh, we think these plates are moving around on top of the planet. Actually, that is solid proof that they must be moving. There are other types of proof too, but that is the best one. So now what you need to do is go on to slide, I think it's 32, and have a go at ordering the process. I think I've kind of gone through the process in some logical steps, but it gives you at least the facts and stuff to write down. If I were you, I'd jot them down. If you want to do a little diagram too, or stick your little pulley thing perhaps into your notes, that would be a good idea. But I hope that helps.